Imagine a world where everything you see, touch, and experience is not as real as you think. What if the entire universe is a grand illusion, an intricate projection designed for us to explore and interact with? This fascinating idea challenges the very foundations of our understanding of reality and invites us to delve into the deepest mysteries of existence. Is the world we see an illusion? Physicists suggest that the universe may not exist the way we perceive it. From a scientific point of view, everything can be a perfect illusion, as if it were created for us. We live in this illusion and explore it. But now we are on the verge of a breakthrough that will allow us to uncover the greatest lie of all time. Is matter really real? It seems so. When you put your plate on the table, it stops and you can absorb food into your body. You will notice that this action works. You digest and gain strength from the food. There is no doubt that the material world exists in one way or another. We can kill ourselves with weapons or rather destroy our bodies in the material world. However, recent studies show that the material world is nothing more than a hollow projection created for us to experience as the protagonists of this world. We may be more than what we see, perhaps something very different from a mortal body with a brain and a heart. Until now, scientists believe that when the body is destroyed, a person dies, and some scientists believe that this must be the end of life and existence. But there is evidence that our bodies are just condensations in three-dimensional space, perhaps controlled by what religious people call the soul. Similar to the movie Avatar, we could simultaneously exist in another world, sleep there and dream about our lives as avatars on Earth. Then this world would be nothing more than a puppet show. In a way, we ourselves are the actors and the main characters, but most of us are not aware of it. The theory of relativity is not the measure of all things. Was Einstein wrong in proposing the theory of relativity? Some modern theories, such as quantum gravity and string theory, challenge his assumptions. Relativity does not work at the microscopic scale. Quantum physics and relativity often contradict each other. There must be some level or levels that unify the two. There is no other way, because quantum theory is a theory of the world of the smallest particles, quanta of light, and these are the building blocks of all great phenomena. Einstein's theory of relativity treats the universe as space, stars, planets, and the impact of visible objects on the world. But these objects are all made of light quanta and do not behave as if matter were real. Einstein's theories are still fundamental, but science is always evolving. We are now at a point where this type of physics is no longer developing. The latest discoveries from the James Webb Space Telescope can no longer be described by old physical theories. Einstein's conception of space and time is certainly incomplete. Quantum mechanics reveals phenomena that his theory cannot explain. Black holes and singularities contradict general relativity in important ways. The existence of dark matter and dark energy remains a mystery. Space and time may not be fundamental quantities, but they are much more flexible than previously thought. The connection between gravity and quantum mechanics is also unclear. Recent findings suggest that gravity may not be a force at all, but rather a curvature of space-time caused by mass and energy. Some scientists suspect that space and time themselves may be made up of tiny, quantum-like structures. These structures may behave in ways we do not yet fully understand. They may possess some kind of intelligence or represent some form of power or life that we cannot yet imagine. There is evidence that the physical forces of the universe have changed over time, suggesting that the universe is undergoing some kind of evolution, just like life. Einstein's work was a milestone, but the search for a unified theory continues. However, if the universe turns out to be a mutable void projection like ours, then we have little chance of reaching the truth using the methods of old physics. We will need metacognition or entirely new sciences to unravel the mysteries of the universe. How does the void projection work, and who created it? If everything is just an empty projection, where did it come from and how is it structured? This idea is basically based on the concept that all the information that makes up our three-dimensional universe can be stored on a two-dimensional surface. This theory has its roots in quantum mechanics and general relativity. Quantum mechanics has discovered that quanta are nothing more than incredibly changing information carriers. They can become a table and thus transform the information of a table into planet Earth, or they can become any other matter. But even if they do form spontaneously, they have the fascinating property of instantly vanishing if not measured or observed. In terms of quantum physics, this means that your board will disappear when you or no one else is looking. Sparse projection theory assumes that our three-dimensional universe is just a rather loose projection of the information stored on a two-dimensional surface. The idea originated with physicists such as Gerard and #039, T. Hooft and Leonard Susskind, and was first proposed in the late 1970s. The key was observations made near a black hole, which demonstrated that the amount of information contained in a given volume of space is limited by the surface of this volume, not by the volume itself. This contradicts the classical understanding of information in space and could mean that the spatial dimensions themselves may be wandering phenomena controlled by deeper levels of physics. In practical terms, this means that for our known universe, all the information needed to construct and maintain this projection is theoretically stored on a two-dimensional surface at the edge of the universe. This information is then projected in such a way that three-dimensional space with its physical objects and physical phenomena appears optically. The universe of pure consciousness, our brain, plays another important role in this situation. We can only perceive the world and the universe through our brains and senses. In fact, we don't see what is actually happening outside. We only see what our brains allow us to see. In a three-dimensional universe, gravity is the result of information projection from a two-dimensional surface. This means that gravity is not really a force in the traditional sense, but rather a dynamic property of the three-dimensional projection. In a three-dimensional universe, we play an important role as conscious observers. We can be both experimenters and creators. It has not been scientifically proven that a table actually disappears when no one is looking, and we cannot verify it with an experiment, because the camera we use to observe it would be equivalent to a ruler that maintains the shape of the table. Another interesting idea in this context could be the role of consciousness. Scientists still do not really know what consciousness is, but it certainly plays a role in the formation of quantum, from wave state to particle state. It could be that the entire universe is imbued with some kind of consciousness that shapes and sustains it. Our consciousness is just a part of a larger whole of consciousness, and we are co-creators of it. But we don't have to worry about the table being a table. For example, does the speed of light matter? Remember the lesson in school about the speed of light being a measure of everything in space? Einstein spent his life studying the forces and phenomena of the universe and came to the conclusion that all phenomena and forces are dependent or relative to each other. Time depends on the position of the observer. Acceleration affects time, and the speed of light is thought to set absolute limits. But it would be a mistake in our physics if the nature of light were completely different from what we have so far imagined. This would mean that all our observations and conclusions over the past 100 years have been wrong. The light we see is made up of quanta, and we now know that they behave in very erratic ways. So how could the speed of light be a stable measurement? It is possible that we have created limitations through this perspective and have built up a false picture that we now have to correct. In reality, light may be much more dynamic and variable. But what does this mean for our observations of the early universe? If the speed of light can actually vary, then we would have to completely rethink our models of the evolution of the universe. Observations of the cosmic background radiation have so far given us information about the early universe based on the assumption of a constant speed of light. The variations could mean that all our distance and time calculations are wrong. Our estimates of the age of the universe and the rate at which it is expanding would then be wrong too. This could explain why the Webb telescope is showing us galaxies that are so old they don't even exist. We usually measure the age of galaxies by looking at the redshift of their light. As the universe expands, the light stretches out and becomes red. However, if the speed of light is not constant, then our measurement of redshift is also incorrect. Finally, this does not mean that Einstein, Hubble, and all the others who built our cosmology were imposters. They simply provided the best possible work and explanations for their time. They seemed to work very well for nearly 100 years. But it now turns out that these theories are incomplete and we need to expand our science to new dimensions of truth. We can explore the three-dimensional universe with our minds alone, but we still need to learn the techniques to do so. Think about it. In the 1970s, there was a man with supernatural sensory perception who could only observe Jupiter through his inner psychic vision. Ingo Swann's work is often overlooked today, but Swan described the planet and its atmosphere almost perfectly and even saw its thin rings, which were only discovered in 1979 by the Voyager 1 probe.